Okay, we're going to do 3 parts here on how to solve truss problems, and you should have 2 pages of notes along with these 2 little pages. I'm going to go over these first. You should glue these into your notebooks. In order to solve these truss problems, a truss problem looks like this, we have to make some assumptions. These do simplify the problems a lot, but they make it where we can do our beginning calculations on trusses. And the first one we do is that members are perfectly straight. It means that our loads will go straight along the axis. In real life, no matter how well we build something, it's not perfectly straight, but those kind of considerations are taken care of later in the design process. Also, all loads are at the joints. We assume that they're always at the joints, which are these corner points or joints. All joints are pinned and frictionless. We assume that these are pinned because, again, it eliminates moments inside the joints. We assume the members themselves have no weight. Basically, we're assuming that how heavy the members are is very light compared to the loads that are going to go on the members, so we assume they have no weight. If you were really using this for an engineering calculation, you'd later go back and put the weight in once you had decided how big of members you needed. And the members can only experience tension or compression. Because we just have them pinned at the corners, we're assuming that they don't have any members within, any moments within the members. So those are our basic assumptions. It simplifies how hard these problems are. The other paper you have there talks about the reaction forces at the end, which is the first thing we're going to do. You have several different situations which you can have. I'm going to zoom in. The first one is that we can have a hinged support, or we also call this a pinned support. It's usually represented by a triangle, and on our picture here we can see one right here. This little line with the little hash marks below it just show that it's sitting on the ground, that it's attached. Or we could have a roller support, usually by a circle, and we can see here that's a roller right there. Whenever I have a pin joint, I replace it with 2 reaction forces, one in the X and one in the Y. And when I have a roller support, I just replace it with 1. If I have a fixed support, meaning this is completely attached, then I would replace it with the 2 reaction forces and the moment force at the end. Remember, our trussers are not going to have moments and at the reactions. And then there's just a cantilever here because there's no support at this end, so it's just whatever our weight is. There's no reaction force there. And then finally, we could also see that instead of drawing a circle for our roller support, sometimes we draw it like as a triangle that looks like it's on roller skates. This is just the same as this one. And this is another way they sometimes draw it, as like a triangle, but kind of has a rocker underneath it. But again, this is just the same thing as the roller. So both of those just have one in the vertical. So this is just to remind us about our joints. And that's basically the first thing we're going to do. So we have 2 problems here. And we're not going to do these whole problems, the whole page in one shot. We're going to kind of break it into steps. The first one is you're given the problem, and then we need to draw a free body diagram, FBD, free body diagram, and put our reaction forces on there. So the first thing is I'm going to repeat the shape over here. And this doesn't have to be exact. And I do want to put the dimensions on here because I am going to need these dimensions again. If I wanted to find this missing side, I could use Pythagorean theorem to find it, but we're not going to need that side. And I also want to put the loads that were over here in my original problem back on here. And I want to go ahead and label the corners the way I already have them labeled. That way when you do the next steps, we have everything labeled. I could put the 45-degree angle here, but I'm not going to need that. Now I need to put these reaction forces on here. So basically all I did was copy it so far. Now I'm going to actually do the reaction forces. This is a pinned joint. So what do I have there? I have 2 different reaction forces that are going to go there. When I add these reaction forces, we're always going to put them going in the positive directions. Just think of a coordinate system. Y is positive going up, and X is positive going to the right. So when I start, we're always going to start off with them going that way. You'll see in the next step what happens if they actually go the other direction, but we're going to start with that assumption. It goes up here, so this is CY, and this one goes in this direction, CX. So those are both starting in the positive direction. Here at A, I just have a roller support, so that's just going to go in the positive Y direction, and we're going to call that one AY. That's all it is for the first box. I'm going to do it on the other problem as well. You should glue these notes into your notebook, but I haven't glued them in just so it's easier to show you on the video. So here's our other problem. I'm going to do the same steps. Step 1, redraw the problem. This one you'll notice it's actually attached kind of like it's hanging off the wall. Maybe this is a bracket that supports a sign or a lamppost or something here. So I'm going to just redraw it, put my links back on here. I'm going to put my original weights on there, my loads. I'm going to label it A, B, C. And when I grade these on your knowledge checks, I'm going to be looking for all these parts. Okay, so this one is a pinned joint, so it's going to have 2 reaction forces there. And I'm going to remember what directions are positive. So I want my Y to be in the positive direction, so that's CY. And I want my X to be in the positive direction, so that's CX. And then this one is at corner B, and it's a roller joint, so I want that one to be BX. That's all there is to this part. Okay.